Thank you. I want to first and foremost thank the organizers for putting together this conference and giving me the chance to speak. I am going to talk about vertex algebras, so everybody who was here very recently heard Clay give you some of the lowdown on these, although then he said other interesting things I don't understand. For the most part, what I'm saying is going to be related to a paper that just appeared the other day with my collaborator Leonardo Rastelli, and it was mentioned before that a lot of the sort of foundational work on this stuff was done by myself with Leonardo and with Balt van Rees and with Wolfgar Pilaers and Madalena Lemos and Pedro Leando, some of whom are here. So I'm going to start out with some very general comments. I am, I guess, obviously going to be discussing algebraic structures that are associated with n equals 2 superconformal theories in 4 dimensions. And although my talk today isn't going to focus on this, I just feel contractually obligated to mention this because of what I do with the rest of my time when I'm not posing as a mathematician, that these algebras that we're talking about are really some sort of weak shadows of some really interesting and complicated full CFT operator algebra that very little is known about. And so a lot of the ideas that I'm going to be using and sort of the motivations come from trying to more generally sort of develop algebraic tools for attacking these theories in general that might someday give us access to sort of the full person of these theories instead of just these shadows. And sort of the relevant information for thinking about these things as algebras, both the big thing and the little things, is the so-called CFT data, which is some list of local operators in these theories along with OPE coefficients that tell you how you multiply them together in this schematic way that's illustrated. But it's specific subsets of this CFT data that make themselves known through these sort of more tractable algebras that I'm going to be talking about. And they're sometimes recycled sort of through various algebras. And that's going to be one of the main points, is that I want to sort of understand how these things get recycled. So to go into marginally more depth than Clay did about the actual structure of these operators in general, n equals 2 superconformal field theories have an SU2,2/2 superconformal symmetry algebra. And the operators, the local operators in them, are organized into certain nice representations of them. And usually when we talk about them, we further organize them in terms of this subalgebra that I've written, where SU21 and SU22 are the left and right Lorentz groups or rotation groups in 4 dimensions. And the others are R symmetries, and R sub E is the real line energy, the algebra generator. So we label local operators by their charges under the Cartan subalgebra of this thing that I wrote down. So they have energy, they have 2 spins, they have an SU2R charge and a U1R charge. And importantly, in addition to these things that I wrote down that are in the ordinary conformal algebra plus some extra R symmetries, there are these supersymmetries. There are 16 nilpotent fermionic symmetries in any one of these superconformal models. 8 of them are so-called Poincare supercharges that are labeled by Q's, and the other 8 are so-called superconformal or special conformal supercharges that are labeled by S's. And in terms of these supercharges, we can construct simpler algebras out of this full-fledged mysterious OPE algebra of the theory, usually by passing to some sort of cohomology with respect to the supercharges, or something like a cohomology. And so I'm going to run through these real quick, sort of what I consider the main ones. The first is the Coulomb-Cairo ring that isn't going to make a big appearance in this talk. It's built precisely out of the operators whose energy is equal to their U1R charge. And as an algebra, this thing is a commutative associative C algebra. As David Benz-V said, there's some more structure, but you sort of have to go outside of the operator algebra to see it. And in general, in examples, this is a freely generated algebra, and so there isn't that much to do with it if you are only studying it at the level of an algebra of local operators and not going to these higher things you can do with line operators and whatnot. And these are specified by sort of being the things that still live around, that are still around after you do the Donaldson-Witten twist and pass to the cohomology of this DW supercharge. Okay, closer to what I like spending my time on is the Higgs chiral ring. So these are similar to the Coulomb chiral ring in that they're specified by their energies being roughly equal to their R charges, this time the SU2 R charge. And generally speaking, this thing is a commutative associative Poisson algebra. And in fact, it is the coordinate ring of a symplectic singularity, which is the Higgs branch of vacua in the theory. This thing is really a hyperkähler singularity. But when you are focusing on sort of a particular cohomological construction in terms of Q's, you really see it as a holomorphic symplectic space. And this thing is defined in one of these strange ways that I mentioned. It's not really in the cohomology of one supercharge. It's defined via something that I think all physicists are happy with and many mathematicians get confused by when it gets raised, or at least at the one workshop where I tried to talk about this before. It's something that most of us would call the simultaneous cohomology of four supercharges. And because I'm not going to do much with it except use the fact that it exists, I won't talk about it more. But I think it's a vaguely interesting question whether there's something to this and the fact that it sounds surprising to certain subsets of mathematicians, or whether it's just a thing that nobody thought to define before because it's not usually that interesting. There's a slight upgrade of the Higgs chiral ring called the Hall-Littlewood chiral ring. This is defined by a slightly more general energy relation. If little r is equal to 0, then this is an ordinary Higgs chiral ring operator. This thing is also a commutative associative C algebra. It's also actually holomorphic Poisson, although I'm not sure that it's been noticed that it's holomorphic Poisson before recently. And the geometry of this ring is not something that has really been well understood. It's something like, spec of this thing is something like a fermionic coherent sheaf on the Higgs branch. And this is, again, defined via this simultaneous cohomology construction, but with 3 supercharges. Finally, there's well, not finally, semi-finally, there's a thing that doesn't really have a name, so just for today, I'm calling it the Schur algebra. It's the algebra built out of these Schur operators that Clay was talking about. So Schur operators are ones whose energy is defined to be equal to 2r plus their spin. And structurally, this thing is some commutative vertex algebra, which is not all that interesting a thing usually. It's just some sort of commutative associative algebra with derivation. But it's actually a little more. It's a vertex Poisson algebra, which gives it some extra structure. And the geometry of this thing, I think, is almost completely unstudied, perhaps outside of people who have talked to Kevin Costello plus Kevin Costello. And I think that this thing is something like the coordinate ring of the derived symplectic quotient of the infinite jet scheme of the representation space that defines the matter content of a Gates theory. And you maybe by the end of this talk will understand why I think it would be interesting to sort of know what these geometries are, because we're going to try to work our way back from something else. And this thing is defined as an honest cohomology. These operators are the things that are in the cohomology of this so-called Schur supercharge here, which is the thing that gets picked out if you do the holomorphic topological twist, which goes back to work of Andre Johansson, and Anton studied it later, and I think the person doing the most with it in recent years has been Kevin. So those constructions I only wrote Q in all the slides, so those are all things that you can do in any n equals 2 quantum field theory. You can do more when you have these extra supercharges called S's that I mentioned before. And in particular, there's this vertex algebra that Clay announced. So this is not a commutative vertex algebra, it's like a good vertex algebra. And in fact, it turns out to be a quantization of that commutative vertex algebra. So this is like the better version of it. And again, you get it by an honest cohomology, but this time it's a cohomology with respect to a supercharge, which to certain people looks slightly unfamiliar because it's a combination of an ordinary Poincare supercharge and one of these things, S's, that you only have in a superconformal theory. And I'll mention, as many people have noticed, that it's certainly the case that there's some sense in which you can realize this thing not by saying Q plus S, but instead by saying the words omega background. If that's true, it's not the usual omega background in the sense that everybody knows at least one omega background for 4-dimensional n equals 2 theories. And I'm under the impression that there's some amount of progress, although I can't speak to the amount, on really understanding this as an omega background by Dylan, Kevin, and Davide. So this is the vertex algebra that I want to start with. This is the main object of my interest. So let me just take a couple slides to review in the sketchiest possible way what these things are and some of their terminology. So for my purposes, as somebody who was trained as a physicist, a vertex algebra is just what I recognize as an OPE algebra in 2 dimensions, which is meromorphic. So it looks like what I wrote, where the dependence on positions appearing in the OP of 2 operators only depends holomorphically or meromorphically. A standard thing that one then does is then you expand these vertex operators, these O of z's, as some sort of Laurent series, where the individual terms appearing in the Laurent series act on the space of local operators that you could insert at a point, which without loss of generality you take to be the origin. And in terms of this, you sort of have a simple realization of this more general notion of a state operator map. A given operator at the origin associates a state that you get by acting with this particular mode in the Laurent expansion on the vacuum state, which is the thing called omega. And similarly, you can get the derivatives of O by acting with these lower modes. And on the off chance that there's any really hardcore mathematical vertex operator algebraists here, I apologize, I'm using the physics moding, so there's an H here instead of a 1. So just so we all know the words, there are some operations that you can do in a vertex operator algebra other than just doing the OPE. There's some sort of smaller things you can do. One is to take just the normally ordered product, which can be defined in various ways, but it amounts to taking 2 states and defining the state that you get by acting with this particular combination of endomorphisms on the space of states. This thing is generally a non-commutative and non-associative algebra, so on its own one doesn't do many things with it usually, except just use it to construct other operators. There's also a secondary bracket. There's actually infinitely many brackets, but there's a secondary bracket that's particularly important, which is just defined by adding a +1 here. So this is the same thing as taking the OPE of 2 operators and just picking out the simple pole. And you can pick out higher poles, and that gives you other brackets as well, but this one's good enough. And to keep going with terminology, there's a notion of a strong generator in a vertex operator algebra, and this is some operator that you can't write as the normally ordered product of anything else, and that is not a derivative of something. And these are useful because then you can build all of the operators in your theory, or all of the states in your space of states, by taking normally ordered products of these strong generators, possibly with relations. So I'll just mention, because in the rest of the talk I will implicitly assume it, that we are under the impression, based on examples, and surely things want to be nice, that in all of the vertex operator algebras that come out of 4-dimensional n equals 2 superconformal field theories, you have a strongly finitely generated vertex algebra. So you only have to list a finite number of these strong generators. And this is useful if there's anyone who likes to bootstrap W algebras in the audience. This is useful because this means that if you want to fix what the algebra is, if you have an opinion about the list of strong generators, it's a finite algebra problem. You can put it on a computer, you write down the most general singular OPEs that you can write down, and you solve some Jacobi identities. Okay, so now I'm going to say a little bit more about sort of the construction of this vertex algebra in detail, because that's going to have some bearing further on. So the vector space, as people have probably concluded, is the space of sure operators in the superconformal theory. That gives us some infinite dimensional vector space, which is the state space for this vertex algebra. And then to get a operator that deserves to be a part of this vertex operator algebra at some general point in space, you have to do it via a so-called twisted translation operation, which looks like this. So in particular, I didn't say it out loud before, but notice that this is a translation in z and z bar and not other directions. So in order to get a local operator that exists well in the cohomology of this appropriate supercharge, you need to only move it in a single complex plane and leave it at sort of 0 in the transverse plane. And what this twisted translation is doing for you, if you work it out, so this r minus here is the lowering operator of SU2R, and it's a fact that sure operators are always in the highest weight state of their respective SU2R multiplets. So if you write a basis with indices, alpha, 2r of them for a spin r representation of SU2R, then the actual operator that you get at a given point is some goofy linear combination of the highest weight plus z bar times the next highest weight plus z bar squared times the next highest weight, and so on. And this is what you get for dealing with the cohomology of one of these Q plus S supercharges instead of a nice Q supercharge. And as a vertex algebra, as a vertex operator, the conformal weight of this, so sort of the thing that controls the powers of z that appear in the denominators of these OPEs for this thing, is given by E minus R, which is R plus J1 plus J2, which is the thing that appeared in the exponent of Q in this expression that Clay wrote for the Schur index. And then the fact that doing this gives you something which behaves meromorphically at the level of cohomology classes is something that just follows from sort of conventional manipulations of the superconformal algebra. Oh, sorry, the L's are the holomorphic and anti-holomorphic derivatives in Z bar planes. So if I didn't have the R minuses, this is just the way that I would move an operator around. They're called L's because they live in the SL2 times SL2 bar subalgebra of the global conformal algebra. Okay, so now I have a construction, and I want to say something about sort of the general structural properties that these algebras have. If you know that if you know I'm going to give you one of these vertex algebras that did come from a four-dimensional theory, what do you expect? What sorts of nice properties will it have? Some things follow nearly immediately. First of all, from the expression for conformal dimension, we know that it's a half z, at least, sometimes integer, but at least half integer, graded algebra. But the half integer grading is uncorrelated with parity, so you can have half integer graded bosons and integer graded fermions. If your four-dimensional theory is local, meaning that it has a stress tensor, or that's what I'll take as the definition of locality for this purpose, then that means my vertex algebra V will have a vertex subalgebra, which is the Virasoro algebra, at central charge minus 12 times the C conformal anomaly of the four-dimensional theory. And as Clay mentioned, that means that the Virasoro central charge is always negative. If I have a continuous global symmetry in my theory, so if I have some conserved currents in the four-dimensional theory, then I necessarily get a vertex operator subalgebra, which is the affine current algebra at level minus K4D over 2, where K is some number associated to this flavor symmetry in the 4D theory, which again is positive, and therefore these are affine current algebras at negative level. And then some facts about operators that I mentioned in the previous algebras. So I have these Hall-Littlewood-Cairo ring operators that I mentioned before. Those are lying around in my list of operators in my theory. And Hall-Littlewood-Cairo ring operators are in particular Schur operators. So they have some life within the vertex algebra. And in particular, you can show that anything which is a generator of this commutative ring, the Hall-Littlewood-Cairo ring, will be a strong generator of the vertex algebra. And furthermore, anything which is a Hall-Littlewood-Cairo ring operator at all will give you something which is primary with respect to the Virasoro subalgebra. And then there's this formula that we saw before, which tells us that we actually know quite a bit about these algebras, or at least about the spectrum of these algebras in many theories, because there's been a lot of work done on this Schur index. This sub SCH means I'm talking about the limit of the Schur index that Clay was talking about. And finally, a very pedantic point that nevertheless for some certain people might be meaningful is that these vertex algebras have no null states. So that's something that a physicist would always assume, but not everybody would always assume. Meaning that you have this vector space V, and there's actually a non-degenerate bilinear form on it that comes from taking two-point functions with appropriate sort of partner operators. And that means that none of the operators can have regular OPE with every other operator. So there's no nulls. Okay, so those were all things that in practice are not that hard to see, and they're not that hard to check in examples. Now I'm going to talk about some structure that's harder to check in examples. So in particular, we know from where the operators come from that this vector space V of Schur operators is triply graded, sort of meaningfully triply graded by the conformal dimension, which we'll use this H convention for the conformal dimension, by their SU2R charge, and by their U1R charge. But the OPE violates the SU2R charge, because the way I built these twisted translated operators was I took the highest weight and added the lower weight and then added the lower weight. So my OPE doesn't give me a graded algebra on this thing, it gives me a filtered algebra because the violation is always in one direction. So if I define filtered components this way, so filtered components of fixed conformal dimension in U1 R charge that have SU2 R charge up to some fixed value, then my OPE preserves that filtration. And also I can ask how these sort of weaker operations act with respect to this filtration. So the normal ordered product is filtered in the naive sense, so it just adds filtered weights. And this secondary bracket is also compatible with the filtration as an operator of degree -1. So something that starts out in filtered component R1 and R2 goes to R1 plus R2 minus 1, and it actually does the same thing on the conformal grading. And this is what's known as a good ascending filtration on a vertex operator algebra, which is a condition that I think was defined by Haisheng Li. And in particular, that implies something which is not that hard to just verify by hand, which is that if you take the associated graded of this filtration, then you will recover a vertex Poisson algebra. So again, that's something with a commutative OPE, but has, I didn't define it before, but has some secondary bracket, which is the remnant of this secondary bracket that I used here, which gives you some sort of a Poisson structure. And indeed, you can just check from the construction that this associated graded that is a vertex Poisson algebra, as a vertex Poisson algebra, is this thing that I called the sure algebra before. So that's the sense in which this non-commutative vertex algebra is the quantization of the commutative vertex algebra. And once you have this commutative thing, you can further restrict. So it's trivial to get back to the other things that I mentioned, starting from this commutative thing. So you can just restrict on the nose to subspaces where H is equal to R, or H is equal to R plus R, where you can see on the slide what I mean by upper or lower case. And that thing will, as commutative Poisson algebras, give me this Higgs branch or this Hall-Littlewood chiral ring. So this is great in some sense if I have this vertex algebra associated to a 4D theory plus this filtration on it, I can get a lot of physics back. I can get these other things that I spent the last 10 years of my life caring about. And I should say here, additionally, I mentioned before that all of this is secretly part of a plot to attack sort of more the full body of the SCFT. And if you want to use the information from these vertex algebras to attack the full OPE algebra via the conformal bootstrap, this filtration is super important for reconstructing sort of the detailed conformal data associated to these operators. But there's a problem, at least at the moment, which is that I don't know how to construct this filtration in an intrinsic way. So if you give me a theory and you tell me everything about it already, then I can construct the filtration. But if you tell me the theory you care about has an associated vertex algebra, which is this crazy W algebra, I don't know how to use W algebra data to construct the filtration. And there can be, and in fact, in these cases are multiple good ascending filtrations, so it's not like the unique one. So maybe there's no intrinsic way to get this, although I think that's too pessimistic. I think eventually we'll understand it. But for the moment, I want to consider an easier problem. Instead of constructing the full filtration, I just want to jump to the end. The last thing I was able to do with the filtration, if I had it, was get myself back to the Higgs branch, which is sort of a nice, very geometric space that I associate with my n equals 2 theories already. So to do that, I don't need the whole filtration. I need less, so let me say what I need. I need to understand some bigger subspaces. So this VH bar is the subspace of the space of sure operators, which are not Higgs branch operators. It's an easy enough thing to define. And you can define it in terms of the filtration this way. So it's the set of filtered components whose R charge starts below their conformal dimension. And then I can define the Higgs subspace. This is just the set of Higgs branch operators in my theory. And that's canonically isomorphic, obviously, to the full set of sure operators modulo the Higgs branch modulo the not Higgs branch operators. Those are things that, so I just said I don't know how to build the filtration, but these are things that require the filtration. But nevertheless, I can define them. There's another thing that I can define, which is actually intrinsic to the VOA. It's a classic construction, I think due to Zhu, although it was probably maybe used earlier than that, called the C2 subspace. And this is the subspace of states in the vertex operator algebra that can be built by acting with a derivative of one field on another field in the normal ordered product. Remember that derivatives give me these extra minuses. And it turns out it's not hard to verify that this C2 subspace and it's even easier to see that this sort of non-Higgs subspace are two-sided ideals for a normal ordered product. And so we have this kind of descending chain of ideals. And there's even more. You can check by direct calculation. It's not that hard. That the commutator and the associator with respect to the normally ordered product are also in this C2 space, and therefore inside of the not Higgs space. And also the symmetrizer and the Jacobiator of the secondary bracket are in these subspaces. And therefore, when you pass to the quotient with respect to C2 or with respect to VH bar, you get some algebra which is a commutative associative Poisson algebra. That's just built into it all. And the one that you get on V mod C2 is intrinsic to the vertex algebra, and the one that you get on V mod H bar is not obviously intrinsic, because to define VH bar I needed the filtration, and I don't always have the filtration. So this one that's intrinsic has a name. It actually has several names. People call it Jou's C2 algebra, or Jou's commutative algebra, or the C2 algebra. I'll probably use them interchangeably. And on the right, so we get that. We get that intrinsically. This is something you can get if you're good at doing computations in vertex algebras. And we know from the four-dimensional construction that if we identify this other subspace and take the quotient, then we're going to get back this Higgs-Cairo ring that I already have opinions about. And the question is, what's the difference? Or if I'm planning on trying to get back to the Higgs-Cairo ring, the question is, what's the difference? Well, just simple like vector spaceology tells me that there's some ideal inside of C2. What did I write? Right, there's some ideal left in the C2 algebra, which I can quotient by that will get me the Higgs branch Cairo ring. It's just defined as the quotient of the non-Higgs operators by the C2 operators, and I want to know what that is. So a lot of this wasn't actually that deep, but I've sort of turned the whole problem of saying how do I get from intrinsic to not intrinsic to the question of what is a single ideal in this particular algebra. There's some good ideal. And I don't have a theorem that tells me what the ideal is, but there's an observation you can make, which is that the Higgs-Cairo ring is expected to always be a reduced commutative C algebra because it's just the spectrum of some affine variety. So in particular, it shouldn't have no-potent elements. On the other hand, the C2 algebra generally has no-potent elements. So it has to at least be the case that the no-radical, the ideal of all no-potent things, is somewhere in this ideal I care about. And so because I like making guesses, you will just guess that the ideal must just be the no-radical. That gets rid of the thing that I know is wrong, and so surely that will leave me with what's right. And okay, this turns out to be a conjecture that then sounds supernatural because you find out that there's this amazing guy, Tomoyuki Arakawa, who's been doing like parallel work for the last 6 years, which is very much related to our own work, without using any of the physics words, which is the statement that this Higgs branch, which is the spectrum of the Higgs-Cairo ring, should then be the spectrum of the reduction of the C2 algebra, which is what Tomoyuki Arakawa has named the associated variety of the vertex algebra. Yes. And just to introduce another word, because so now we can already identify some nice properties. We know that for the vertex algebras we care about, the Higgs branch is supposed to be some hyperkähler cone, and so in particular it's supposed to be holomorphic symplectic, and that's a nice property that an associated variety could have, and so Tomoyuki gave it a name, which is, he calls it quasi-Lie. Okay. So let's see examples. So that's the guess. Can we just check that this works in the most basic sense in simple examples? So the first case is to consider when this C2 algebra is actually finite dimensional. So in that case, the whole thing is no-potent. In that case, if you have a situation where your C2 algebra is finite dimensional, or when your C2 algebra is finite dimensional, then the algebra is called C2 cofinite. C2 cofiniteness is a necessary condition for a vertex algebra to be rational. So we see a neat thing, which is that if we have any superconformal theories that are supposed to have a rational vertex operator algebra, of which there are some, then it has to be a it has to be a theory that has no Higgs branch, which is a special thing. Most superconformal theories that we're interested in have non-empty Higgs branches. And so there's an example of these. Clay mentioned the first of these examples, which is the n equals to 1 case. The so-called A1, A2n, Argyres-Douglas theories have been conjectured originally on the basis of central charges and subsequently on the basis of indices to be the Virasoro algebra at the level relevant for the 2n plus 3 minimal model. And for those, you can compute the C2 algebra. It's just generated by the stress tensor. The only strong generator of the Virasoro algebra is the stress tensor. But then you get a relation from the famous null state that makes this an interesting value of the Virasoro algebra, which in particular sets t to the 2n plus 2 equal to 0. The Poisson bracket's trivial. And this means that when you mod out by the no radical, you get nothing, which is what you were supposed to get. So good, it works. And this is the remark I made before. I don't know if anyone else, it appeals to me that it turns out that these C2 cofinite vertex algebras, which were in some sense sort of supposed to be like the good ones to study for a long time in the study of vertex algebras, turn into this obviously like very special case of these vertex algebras associated to conformal field theories. So we're getting some prediction, which actually was already anticipated because I'm not doing this 20 years ago, that there is a much bigger class of vertex algebras which generalize the C2 cofinite ones that should still have some good properties. And we'll see more about those good properties. Okay, so I will go quickly through the other examples. I'm not going to read out in words what I've written on the lines, but this conjecture also immediately passes tests for the other easiest Argyres-Douglas theories to analyze where there were conjectures about the vertex algebra. So these A1 d odd cases are supposed to be associated to affine vertex algebras associated to the algebra SU2 at these particular levels, which are admissible levels in the sense of Katz-Wakimoto. And you can check that the C2 algebra is generated by the moment maps, or generated by the things that descend from the currents in the vertex algebra, modulo an ideal that looks like this, where omega is the quadratic Casimir built out of the currents. And this tells you that omega is actually no potent already, so when you quotient by the no radical, you just get this thing that's modded out by the Casimir, and that's the same thing as C2 mod Z2, which is the right answer. You can do examples associated to the so-called generalized Brzezinski-Polyakov algebras and get the canonical singularities as Higgs branches. This is the simplest case where you get, that's supposed to be C2, obviously, by the way. You get C2 mod Z3. More generally, you get C2 mod Zn. And I've written all of this out just to make it clear that you're doing something in going from the C2 algebra to the reduction. It's you're really sort of missing something when you do what was intrinsic, and you're getting rid of real stuff when you do the reduction and throw away the extra stuff. Okay, so that's the conjecture, and we have lots of examples now where it's true, so it's probably true. So let's consider consequences, assuming that this is always true. So in particular, this tells us that any strong generator of our vertex algebra that is not a Higgs-Kauer ring generator has to be no-potent in the C2 algebra once we pass to the C2 algebra, because once we mod out by the no-potents, we have to only have Higgs branch stuff remaining. In particular, this includes the stress tensor when it's a generator, and by an analogous argument, even when it's not a generator and it's constructed as like the Sugawara vector out of affine currents, it nevertheless has to be the case that the stress tensor's image in this C2 algebra is no-potent. And it being no-potent means that there's a null vector, a non-trivial null vector that I can write down in my vertex algebra that looks like L-2 acting some number of times on the vacuum. This is k times the stress tensor in the C2 algebra, plus something where that thing is in C2. So this is a null vector that tells me that L-2 to the k, which doesn't look like it's in C2, is actually in C2, once I take the simple quotient. And we're accustomed, hopefully, from our extensive experience in rational conformal field theory, that when we have these null states, you should try to figure out whether it has implications for the observables in your theory, in particular, whether it implies some constraints on partition functions or correlation functions of your theory. And the standard thing to do with a null vector of this type, which has been studied for a long time, going back to the late 80s, maybe even earlier, if I didn't go far enough back in the literature, is to consider the torus partition function, and to try to impose some non-trivial constraints on the torus partition function from the fact that this vector is null. And in our case, that's going to be telling us that the vacuum character, and so the Schur index of the n=2 theory has some interesting constraints. Now, a disclaimer, I'm about to sketch a proof, and the sketch is going to be of sort of a wrong proof. But there's like a better version of the proof that works, which is due to Arakawa and his collaborator Kawasetsu very recently. But the version that I sketch is going to actually give the algorithm that basically works in all cases. And the point is that there's some obstruction that can happen sometimes that I basically have never run into in very many examples, but it might occur. And their theorem shows that even when that obstruction occurs, you can work harder and get around it. So the point is that I have this null vector. And so if I consider the trace on my vertex algebra of q to the L naught minus c over 24, the usual thing for the torus partition function, and insert the 0 mode of that null vector, I have to get 0, because that null vector is 0. So in particular, because my null vector was written as these two pieces, the part that looks like stress tensors and the part that looks like something in C2, I can set it up as this equality. And then the trick is that there's ways to evaluate the left-hand side and the right-hand side in terms of different operations on the vacuum character to get constraints on the vacuum character. So on the left-hand side, I just have factors of L minus 2, and I have 0 modes. So it turns out that this situation of 0 modes of the stress tensor in the torus partition function, you will be unsurprised, can be turned into differential operators acting on the vacuum character, because the 0 modes of L minus 2s are things like L0s, which are the things that appear in the exponent here. Only it's a little bit more complicated. So you don't get really simple differential operators. You actually get sort of modular covariant differential operators when you do it right, which have some specified form depending on how many copies of L minus 2 you had, and they look like this in general in terms of various Eisenstein series. The right-hand side is a little bit harder, but still doable. If I have something in C2, I know that I'm supposed to be able to write it this way with a derivative acting on something else. And then there are recursion relations that let me replace that derivative with things that are higher moded at the expense of Eisenstein series, which in particular can be twisted Eisenstein series in the case where the conformal dimension of this thing is not integers. So in my case, it can be half integers. So these are particular types of twisted Eisenstein series that can have negative ones here. The form of these things is known. And what you do then is you have something over here that has a positive mode number, and you do a bunch of commutators, and you hope that you either get something, again, that looks like it's in C2, or you get something with a stress tensor. If it's something with a stress tensor, then you can get a derivative. If it's something with a derivative, then you can do the recursion again. And there are obstructions that can happen, and this is the thing that never happens, but if it does happen, you can get around it. So at the end of the day, if you've gone through this analysis and either not run into the obstruction or gotten around the obstruction, what you find is some sort of modular differential equation, either modular with respect to the full modular group if you didn't have any of these half integers, or with respect to the conjugacy subgroup gamma 0 of 2, which is generated by T squared and STS. You'll get modular differential equations with respect to those modular groups, which gives you an extraordinary fact about these Schur indices, which, as Clay said, have been studied quite a lot. But somehow, nobody quite noticed. Okay, I shouldn't do injustice. So Shlomo Razamat noticed a number of years ago that there was something interesting going on with modular properties of the Schur index. And for the very simplest cases like hypermultiplets, he saw exactly what was going on. And then for the more general case, it was very hard to do the analysis. But there was something going on, and this tells you exactly what's going on. It tells you that as long as this Higgs branch picture is right, then the Schur index of any n=2 superconformal field theory is the solution of some finite order linear modular differential equation whose coefficients are polynomials in the appropriate kinds of Eisenstein series. Thus, these Schur indices, of which we have an enormous collection, give us a big source of vector-valued modular forms of weight 0, and they can actually be pseudo-modular in the sense that they sometimes have logs in them. But that's okay. They can have log q's in them. We will see that actually they almost always have logs in them. The Schur index itself does not have logs in it, but the other elements of the vector valued modular form. So additionally, as a practical matter, this is very nice because the dimension of the space of these modular differential operators at fixed weight is finite. So there's some finite number of parameters. And so if you have a Schur index up to order q to the 50, you can check with very little mental work and some computer work whether it solves a modular differential equation, or you can plausibly check whether it looks like it solves a modular differential equation of order up to some reasonably high value. So here's an extremely simple example. So there are these rank 1 F-theory theories. These are theories that you get by putting a D3 brane at a singular fiber of an elliptically fibered K3 in F-theory. And those are labeled by this set of Lie algebras where there's a formal one called A0. And it turns out that for all of these, there's a uniform second order equation that you can write just in terms of the dual Coxeter number. And then once you do this, A0 has to be dual Coxeter number 6/5 formally. And if you then, this is a fun fact, if you then go and analyze the solutions of this differential equation and ask for them to have integer coefficients, then you recover the examples you already had. You had to, but you recover a few extra examples. You recover one that is associated to G2, one that's associated to F4, and one that is goofy, which in some sense is associated to a thing called E7.5. And these are a famous sequence of Lie algebras called the Deligne-Svetanovich exceptional series of Lie algebras. And that's a nice discovery. And there's lots more to say that I don't have time to say about those, but that's a fun mathematical widget. But in connecting to four-dimensional physics, I should admit that at the moment, for F4 and G2, there aren't known SCFTs, and there's actually an argument by Shimizu, Tachikawa, and Zafrir from recently that they can't exist. Although, and I know this is being recorded, so no offense, guys, but I'm not totally convinced yet. I think they might exist. E7.5 definitely doesn't exist as a 4D theory. Now I'm going to flash some data at you. So because it's easy to do these analyses of modular differential equations in characters, as I was saying before. So you can go and take n equals 4 super Yang mills where people know the indices to very high rank, and you can look for these modular differential operators, and you can find lots of examples. You find modular differential operators of the order given here for the appropriate modular group. And then you can look at the solutions. Oh, okay. We'll come back to these conjugate dimensions. You get solutions with some list of weights for the exponents, and the interesting thing is that for a gamma 0 2 modular differential operator, if you have weights that are separated by half integers, or if you have a gamma modular differential operator with weights separated by whole integers, then you're going to get logs, or you're almost certainly going to get logs. And you see that in all of these cases you have that. So these logarithms are generic in these theories. You can also go to very high order for the so-called A1 theories of class S and just see similar themes. Although something you start running into that I would like to understand better is that as you go to very high rank theories, you start running into modular differential operators that have solutions to their initial equation that are complex or rational. And I think that that's a sign that for these high rank theories, you actually get systems of modular differential equations that annihilate the vacuum character, and we're only looking at a subset, but that is to be understood better later. These are all full punctuation. These are A1, so it's all. If you have a good way of producing the indices to high order in Q, it's very simple to do these analyses regardless. For the particular case of the A1 theories, there's an enormously simple expression for the index in general as a function of G and the number of punctures. So that's why I focused on those. So just some comments on interpretation, which connects with Clay's discussion a little bit. The derivation of the modular differential equation goes through if instead of looking at the vacuum character, you're looking at characters of non-trivial modules, if the modules have some nice properties. So if they have finite dimensional L0 weight spaces, and if their conformal dimensions are bounded from below. So a natural guess for how to think about this, the other entries in these vector-valued modular forms, is that they should be the characters of the surface defects. And for some of the simple, for like the classic cases, like these Argyros-Douglas theories that were giving you minimal models and SU2 at admissible levels, this is something you can just check. But more generally, I think it's what you should expect. That said, these conditions of finite dimensional weight spaces and bounded below conformal dimension are not things that you need to demand for a healthy surface operator. So you're likely to be probing sort of classes of surface operators as opposed to getting some super strong statement that like all surface operators correspond to elements of this one vector valued modular form. In particular, one thing that definitely happens is that you can have reasonably nice modules for these vertex algebras that do have infinite dimensional L0 weight spaces. But if you turn on flavor fugacities, so if you grade by an extra sort of global symmetry grading, then the combined weight spaces are finite dimensional. So these things have good characters if you grade for everything, but they will have a bad limit where you turn off the second grading. And in those cases, a couple of things can happen. You can either have finite limits for combinations of characters. This is what happens with the admissible level SU2 affine current algebras. Or you can have some sort of genuine singular behavior that somehow gets regularized, and this is something we haven't understood well enough. But this is actually this I think is the origin of the logs in the generic non-vacuum solutions. Okay, so that's great. Let's say even more. If we have now we have very strong modular control over these Schur indices, over these vacuum characters. And in particular, that means that we can understand very clearly, at least up to computing these S matrices, schematically we understand how they transform under S transformations where tau goes to -1 over tau. So Q being e to the 2 pi I tau goes to Q equals e to the minus 2 pi I over tau. These are non-rational theories. I'm getting this result not from some general considerations, but from the existence of the modular differential equation. So this is like the admissible. I mean, I think the hallmark example should be the admissible level affine current algebras. Those are generally irrational, but they have some good set of characters that transform into each other. But you don't expect the S matrix. You don't expect the Verlinde formula to work for fusion. But there's still some modular S matrix that controls characters. So that's a finite sum, yeah. Yeah, exactly. So the key was the existence of this finite order modular differential equation, independent of my opinion about the representation category of these things. I'm going to get a finite sum, which means I can really look at the expansion of these characters, and let me just get the whole slide on. And I can look at the weight, which is the minimum one, which controls this so-called effective central charge that controls the Q to 1 limit. So this is the so-called Cardy limit. And the nice thing here is that anomaly analysis due to DiPietro and Komargatsky, or really a slight generalization of it that Leonardo worked out with them, tells you that the high temperature limit, so the Q to 1 limit of these Schur indices should be controlled by this combination of the 4-dimensional anomaly coefficients. And so you're getting a relationship between the 4-dimensional anomaly coefficients that includes A, which we didn't see earlier in this talk, to this quantity Virasoro central charge minus 24 times the minimal dimension of the characters that appear in the S transformation. So this tells you the relationship between the A anomaly and these and the smallest of these module dimensions that appear in the S transformation. And if you combine that with the Hoffman-Maldacena bounds, which are some unitarity bounds, so if your 4-dimensional theory is unitary, there's certain bounds on A and C, and this tells you that this minimal module dimension has to sit in some finite range between C over 8, which is negative, and 0. And I'd like to make an observation, which is that in these tables that I showed you, and in fact in almost all examples, and in the counterexamples, I don't think they're real counterexamples yet, it appears to be the case that not only H min is less than 0, but all the h's are less than 0. So it may be that all of the characters that transform in this vector valued modular form have to live in this finite range, which would be, I think, a pretty strong property. And this, not the observation, but this original statement, is already enough to do a cute little test, which is you can just say, let me think of vertex algebras that I like, that I might wonder whether they could be the vertex algebra associated to a 4D theory, and then just look for their h-mins and figure out if it obeys this rule. And the only point of this comment is that that is a non-empty exercise. Many things obey the rule, but there's also things that don't, so there's an infinite set of non-unitary Virasoro algebras that don't obey it, and I believe that Clay and Xu Heng have used this trick to find even more impressive results in the context of affine current algebras. Okay, so I'm about done. I just wanted to show one complete example. So now I've said like a bunch of things you can do if everything works, and now I just want to like go through what happens when you do this in an example. So let's consider everyone's favorite theory, which is n equals 4 super Yang-Mills with SU2 gauge group. In this case, the associated vertex operator algebra is just the small n equals 4 superconformal algebra in the 2D sense at a particular value of C. So this is that algebra if you don't know what it looks like. It actually turns out that for this value of the central charge T, the stress tensor is not a generator. It is the Sugawara stress tensor generated by these currents. But I'm going to leave it there anyway. These G's are the supercurrents. They're fermionic operators of dimension 3/2, which transform in the 1/2 of the SU2R symmetry. So you put this algebra on your computer and start computing norms of states, and you find a bunch of null states that look like this. And you ask, and one more null state at dimension 4, which is of the type that we were hoping for. This is a null state that says that L minus 2 squared is in the C2 algebra. Look at these things. These are all in C2. And then you say, what does this all mean in the C2 algebra? That's my game. I'm going to start out with the full thing, pass to the C2 algebra, throw away no potents. So my C2 algebra, that means, is the thing generated by the currents, by the stress tensor, which is actually a composite, and by these fermionic guys, modulo an ideal generated by these relations, which are just the images of the things that I wrote down before in C2. And you can check what's nilpotent, and you can see that after you mod out by what's nilpotent, you just get C2 mod Z2. So all that's left is the currents, the T. You have a T here that becomes 0 because T squared is 0. So that means that the currents quadratic Casimir is 0, which is again this C2 mod Z2 space. The Poisson bracket comes along for the ride as well, so you get C2 mod Z2 as a holomorphic symplectic space. And then you had this modular null that gave you the T squared equals 0 condition, and you can run recursion on it and derive some modular differential equation, which in this case looks like this. And you can solve it, or more simply, you can solve the indicial equation, and you can find what the weights of the characters are. So first of all, the second solution to this equation has h equals minus 1/2. So that means that you have logarithmic solutions. And here's an advertisement for work in progress. So with Wolfger, we've analyzed this particular case when you turn on flavor fugacities. So this thing has this thing has flavor, and so you can turn on additional grading. And indeed, when you do that, it annihilates this logarithm. So the logarithm is a fake associated with there being a module that doesn't have a good limit where you turn off the extra flavor grading. And then to take the q to 1 limit, because this is half integers, I need to write down the conjugate equation, so the S transformed equation, where I flip the plus 1s and minus 1s in these twisted Eisenstein series. And you solve that, and both modules have h equal to minus 3/8. And you plug that into my equation from before, and you find out that A4T is equal to 3/4, which is something you already knew, but it's sure nice to see again. So to conclude, there are some obvious extensions of this just to get a complete handle on sort of what is going on with all of these modular transformations. The most obvious thing is to include these flavor fugacities. That means that instead of working with modular forms, you're working with Jacobi forms. This stuff can get pretty hairy, but hopefully you'll have a nice story. That should probably be the right set of characters to study their modular transformation properties. Setting all the flavor fugacities to 1 seems like a wrong thing to do. And you can also modify these recursion relations if you want to understand the case where you're not looking at ordinary modules, but twisted modules. And twisted modules are actually something that should come up in physics. So things, even these canonical surface operators in class S can be twisted modules with respect to the vertex operator algebra. And I will finally conclude with some open questions. So the first, which might not even be a meaningful question the more I think about it, but it might be interesting, which is what is the property that controls this number, which is the order of this modular differential equation, which to my mind, as long as this obstruction I was ignoring before never arises, is roughly speaking sort of the degree of nilpotence of the stress tensor in the C2 algebra. It seems to have some power over these modular properties, so I don't know if it might be an interesting structure. However, I should mention that due to recent work by Fredrickson, Pei, Wenbin-Yan, and Ye, it appears that it may be really the case that you should spend more of your time thinking about the set of characters for the flavored thing. And there's some shocking, to me, evidence that sort of the modular behavior of the characters with the flavors is associated with structures on the Coulomb branch, which I haven't said anything about this whole day. Because that's not where I usually work. Another question, I extracted the Higgs branch, I think. I would like to be able to extract the Hall-Littlewood-Cauer ring as well, which was this sort of intermediate ring. That's going to be trouble because elements of the Hall-Littlewood-Cauer ring that are not elements of the Higgs-Cauer ring are usually nilpotent. So my nilpotent trick is not going to work. The Hall-Littlewood-Cauer ring has like important nilpotent elements. So I would really need to do something better. And probably what I need to do is just find a way to construct this whole good filtration. And there's been some work on this by Jaewon Song, which seems to work in some very simple cases. I think that it's going to take qualitatively new ideas to get it in the more general case. But that would A, let us extract these rings more easily, but B, it would actually lead to an enormous number of very strong constraints on these vertex algebras from unitarity. It's very hard to impose the constraints of four-dimensional unitarity on these vertex algebras precisely because we don't have this filtration that lets us like really nail down which operator corresponds to which operator. So, thank you.